So I'm going to spend a little bit of time talking about methane emissions and following and detecting these emissions using, in particular, Sentinel-5P. Just before I begin, a few words about Keros. So I co-founded a company with some friends 4 or 5 years ago called Keros. The idea was to follow energy markets using alternative data and in particular satellite imaging. We're about 150 now, and we're happy to collaborate very closely with some of the great labs we have in Paris, like LSC and Centre Borelli. And since we focus on energy markets, we talk a lot with energy companies, hedge funds, etc. Our first product was tracking crude oil stocks worldwide using SAR imaging from Sentinel-1, measuring the height of these tanks in real time. But the idea is to follow the carbon molecule along its lifetime, and unfortunately, that life often ends in the atmosphere. And so the point of these slides is to show some of our work on methane. And the reason for this is perhaps that methane is one of the lowest hanging fruit on climate change. It's the second largest contributor to climate change after CO2. But until Sentinel-5P and some of these other sensors, we didn't have much data, or at least at a global scale. And now that we have data, you start to realize that a few dozen daily leaks are responsible for the CO2 equivalent emissions of the airline sector. And so in some sense, in terms of action, you have a choice between plugging 30 or 50 leaks every day or shutting down the entire airline sector. Which one is the most likely to happen, right? The other question for Europe is that most of these emissions occur outside of the continent. And so if you're going to regulate these leaks, you need remote sensing, right? And the other important fact to keep in mind about methane is that while everything is compared on a CO2 equivalent basis, typically 100 years, methane has a much shorter lifespan, about 12 years. So everything you do now will have a much more immediate effect in practice, right? So the comparisons are made over longer horizons, but the effects of mitigation will be felt much faster. And that's why methane is such a nice target in some sense. So the graph you see here is taken from a paper by Drew Schindel on the impact of methane mitigation policies. So to be a bit more precise about what we are doing, so what we use as a sort of raw material is the image, the green image you see on the left. And that's an image produced by Sentinel-5P. And Sentinel-5P covers the entire Earth on a sun-synchronous orbit every day at around noon. That's important because at noon there's a little bit of wind, and which means you get an image every day when the weather is not too bad. And the pixel size on the ground is about 5 by 7 now, 5 by 7 kilometers. And the level 2 product from Sentinel-5P gives you total column concentration of methane. So you can directly observe images of methane concentrations worldwide on a daily basis. And that's fairly new. So we could do that at much lower resolutions, maybe in the past, but to have this information with this frequency and this global coverage is something new. And we used it to go and chase a large methane leaks related to oil and gas infrastructure. So the oil and gas sector is a huge producer of methane emissions, and Sentinel-5P allows us to start tracking these emissions and quantifying them. So that's what we started doing, and the very nice and clean plume you see on the left is a perfect sample of the kind of thing we observe. This is perfect weather. It's there for illustrative purposes. Typically, the image is not as complete, but this is basically the raw material. And the idea is that you get images like this all over the globe. You have to detect them. So you get a full picture of the globe every day. You have to detect these plumes. They have a particular shape. Concentration is fairly high, etc. So it's basically peak detection, but you still have to do it every day at global scale with a pixel size that is relatively fine. And then once you have a plume, your job is not over. The idea is to find the source. And so thankfully we have weather information. So we cross-reference weather and the plume image. And on top of that, we have a lot of information on the side. And I'll come back to that in a few slides. We have information about oil and gas infrastructure, and we have many other sensors. And the idea is that the resolution of Sentinel-5P alone does not allow you to go back to the source precisely enough and attribute emissions. But if you cross Sentinel-5P information with other sources, at some point, in many cases, you can start to do attribution. And again, if the weather conditions are not too bad and the source is concentrated enough, there are high resolution satellites that allow you to see methane after a little bit of image processing. And the image you see here is an animation of a plume at the very same location that we observe with Sentinel-5P, but this one is at 20-meter resolution. And you can then see the plume and you can track it down to a particular facility. And in this case, this was in Algeria. And that source was confirmed by the operator itself. So that's the idea. We start by detecting large plumes using Sentinel-5P. And then we need to attribute these plumes to their source using a variety of other sensors. That's another example. A bit more abstract, again in Algeria. So in this case, we also observe a plume. It's actually the same one or the same location. This is a sort of canonical example for us because they reliably produce very clean, large plumes at regular intervals. And so there are a few things you need to do. You need to check for false positives because albedo sometimes can create plume-like effects. You need to check that your plume is indeed aligned with the wind, which is always a good idea. Check for aerosols, etc. So there's a long checklist of things to go through before you can actually confirm that this is indeed methane. And then once you have a plume that you can identify as methane, you have to go back to the source. And you can do that by just going upwind, and you land in a region where the number of sources can still be fairly large, right? It's a 5x7 pixel. You can narrow it down to a few pixels, but that still leaves a fairly large area to check. And the good news is that we have a lot of information typically in that area. And so that's another example of how to do attribution. So this image on the upper right corner is a zoom on the one single area inside the red dot over here. And you see that there are multiple facilities in this region, in this pixel, Sentinel-5P pixel. But if you look with another sensor, and here this is Sentinel-2 in the infrared domain, you can see that at the same time this methane source stopped, flaring started at a particular location. And flaring is something you can see using Sentinel-2, and Sentinel-2 gives you a pixel size of 20 meters. And so you can now attribute the fact that the methane plume stops and the flaring starts is a strong signal that this is probably the facility you're looking for. And so you can attribute the Sentinel-5P plume using Sentinel-2. That's another example where, in this case, we see a plume near an intersection of pipelines of gas leading to Europe. And here, what you can do is that you can use infrastructure to track down the source of the emissions, right? So again, you go through wind data to make sure your plume is well aligned with the wind. You go upwind, you see a couple of a suspicious area, and you start looking for infrastructure in that particular area. And what you detect is a sort of intersection of pipelines. And near this intersection, you see a compressor station. And since there is not much infrastructure in the area besides this compressor station, it's quite likely that this is the source you're looking for. Right, and a final example, this is in the US, in a shale basin. Again, you see a fairly large plume, you go upwind, you get to the source, and you zoom in on that particular pixel. And in this case, you see a number of pads. But the point is that, okay, there are many pads inside the sort of likely source pixel in Sentinel-5P, but you can track fracking and drilling and completion activity inside those pads and correlate emissions with completions. And you see in this case, for example, that there was a recent well completion in one of those pads, and it's kind of likely that the emission you observe using Sentinel-5P can be tracked down to this particular source, right? So you would do that worldwide, and you do that every day, and you do that for a full year. And what you find is a lot of very large sources. So to give you an idea, our detection, the theoretical detection threshold for Sentinel-5P is around 5 tons an hour. Using our methods, we reach something like 10 tons per hour. And so all the dots you see here are methane leak detections above 10 tons per hour, right? So which is a very significant number. The number of detections above that threshold before Sentinel-5P was in the single digits yearly. And so the fact that we saw so many of these large leaks was a bit of a surprise. And you can also see on this map that there are huge discrepancies between different regions, right? So Europe is fairly clean, but that's because we don't have much gas to begin with. But yet we import it, we have pipelines and so on, but they are fairly clean. We see these sources in Algeria. Turkmenistan is a massive emitter. Its infrastructure is emitting methane at high volumes on a daily basis. Same thing for places like Iraq. Saudi Arabia, on the other hand, very large, significant producer, very few leaks. So that's in particular because their regulation on associated gas are fairly tight. And so we observe comparatively fewer leaks, especially compared to the volume of energy produced. We can follow pipelines in Russia using these large leaks, and this is typically maintenance, although the gas could be flared. And we, of course, see all the shale basins in tight oil basins in the US. So lots of leaks and a lot of volume, and perhaps a lot more than people expected when before Sentinel-5P was launched. One thing that this allows to do, it allows to quantify the amount of emissions embedded in gas imports. And if you import a lot of gas and you use this gas to complement renewable energy production strategies, you can, because you don't want to pretend that natural gas is a clean source of energy when its production process is associated with very high emissions. So it's important to differentiate between gas import sources, and we can do that, at least using the methane that's visible from Sentinel-5P. And so that's part of the idea behind these detections. It's to give utilities and consumers a little bit more information on the emissions embedded in the gas they consume. So from a purely technical point of view, just to give you an idea of what the pipeline, quote unquote, looks like and what the detection problem looks like. So Sentinel-5P produces about 300 gigabytes of L1 data every day. If you want to do detection at very fine scale, this is the kind of data you want to use. Otherwise, Sentinel-5P also produces level 2 data, which directly gives you methane concentrations, but is a lot more conservative. And so you're missing some pixels that you shouldn't be missing. But the pipeline will change at some point in the future, but well, it's still a lot of data to process. So of course you need to do most of that processing automatically because you need basically every day to scan for these large plumes. And so the first thing you run on these things is cloud detection, of course, albedo measurement, etc. Then you do a bit of smoothing. And finally, peak detection to identify large leaks, which is essentially spatial anomaly detection. And after that, once you have wind and a plume, you try to go back to the source by basically moving upwind. And at that point, the last thing that remains is to try to quantify the amount of methane you're observing. And the way to do that is fairly straightforward. you simulate, once you have narrowed down to a particular source, you simulate an artificial plume using the same weather conditions that you observe in your detection. And you vary the volume of methane emitted so that the simulated plume matches your observations. And that gives you the rate. So it's a forward model, and it's something you can run at scale on a daily basis. Right, so that's an example where you have a detected plume near a piece of infrastructure. So here, pipelines. You have the wind, the small white arrows, and you simulate an artificial plume using high split, for example, or geochem, and you match the two to get, in this case, a rate estimate at 26 tons per hour, right? Which is big. And so once you have quantified these large plumes, the next stage is to try to attribute them to a particular facility. So in places where infrastructure is very sparse, that's easy. In other places where infrastructure is very dense, like the Permian, for example, this is a lot trickier. And you need to go down to the particular facility, because if you want to do mitigation, you need to know where these leaks are coming from. And this is actually more difficult to do from the ground than from space in many cases. And so it's important to increase the resolution of your detections. And fortunately, there are a number of satellites that give you high resolution images in the shortwave infrared spectrum. Sentinel-2 does, WorldView-3 does, a new satellite called Prisma does as well. So this sort of part of the spectrum is getting crowded at high resolutions. And you can use that to isolate methane sources at a much with much finer details. And so the idea is to use high resolution spectral images in the wavelength of absorption, of methane absorption. So this is the plot you see on the upper right corner. The blue curve is the transmission spectrum of the Sentinel-5P tropomy instrument. And the red and black graphs are these high resolution sensors embarked on Aviaris, or NMAP, which is a German satellite that will be launched in 2021. And so in this case, you try to isolate methane sources with much lower spectral resolution, but much higher spatial resolution. And that means that in particular, you're going to have a lot more false positives on the ground, things that appear as methane but are not methane. And so a lot of the work involved here is things like background removal, anomaly detection, etc., and pruning out all those false positives. The good news is that since, again, these oil and gas emissions are coming from point sources, and particularly in pieces of equipment or infrastructure, and that you can see these facilities at 20-meter resolution, it's very hard to tell if what you have in front of you is an actual oil and gas plume or something that is completely spurious. And the point after that is to go back to the assets on the ground. So that on the lower right corner is a typical example of fortunately enough, these large plumes are not that frequent in the Permian, but still. So this is an example of a plume near a compressor station in the Permian Basin in the US, in a leak that started in July and actually lasted for 3 months, believe it or not, at 5 tons an hour. And so the image on the left is optical, and the image on the right is the same thing after post-processing, background removal, etc. What you're left with is a methane concentration at high resolution. So this yellow plume here is coming from a compressor somewhere here, right? So the good news is that the methane is a lot more visible now than it used to be. And it's visible at resolution high enough so that you can do, and frequently enough so that you can both do high frequency detection of leaks and attribution of some of these leaks. And that should, we hope, significantly help mitigation. And fortunately, it didn't go completely unnoticed, and Europe is fairly proactive on the topic. And this is just a sort of cameo where the Kadri Simpson, who is the EU Energy Commissioner, tweeted our methane detection map when the EU launched its methane strategy in October. And so it seems that regulation will change, but we hope it's going to happen soon. Okay, thank you, and I'll be happy to take questions.
Thank you, Alex. It's both fascinating and frightening to see methane emissions like this.
Yes.
Any question? I see several questions on the chat. Yes, what about methane emits by the melting of pergylitol? That looks very technical.
Yeah, if I understand the question well, that's probably diffuse, and so the rate of emission is maybe lower than that detectable by Sentinel-5P. So I'm not sure if we can see it or not, and we haven't really looked. But this 5 tons per hour threshold is something that we've computed for point sources. For more diffuse sources, we don't really have an idea of where the bar is. We've tried to look at livestock, for example, and we haven't found many detections there. So Sentinel-5P in our case seems to be particularly well suited to these large point sources coming from the oil and gas sector.
Okay, thank you. There are a series of questions about the quality of the simulations, assessments of the simulations based on observations. Can you say something about it?
So there are a few things you can do. So first, we have an idea, numerically at least, of the uncertainty, and it's typically of the order of 30%, and that's just by doing scenario analysis. But otherwise, the other thing you can do is benchmark detections against other sources like flights. So the Environmental Defense Fund, for example, flies sensors with scientific aviation over the Permian on a regular basis. And so the last plume you saw, I can probably go back. No, well, it doesn't matter. The last plume you saw, the yellow one, was actually on a facility that was flown over by EDF and Scientific Aviation, and they also quantified the same plume with an airplane and a much higher resolution and a higher spectral resolution. And they also quantified the source, and the rates match. And so the ultimate test is to simply compare the quantification of several sources and check if the rates match. But I'd like to insist that the quantification problem is nice, and we're scientists and we love to quantify stuff. But the most important problem here is detection. If you see a leak and you can point to its source, you've solved like 75% of the problem. The numbers matter afterwards, but not as much. And so detection is the key here.
And I have a question about this. Do you use algorithms like neural network or deep learning for image analysis in your work?
Not in this case. We might eventually at very high resolutions, but what we do here is really signal processing, anomaly detection, and basically image analysis. And the reason for that is that we need a sort of auditable physical measurement rather than something out of a black box.
I see.
And all of our observations and quantifications are based on physical models. And so I'm not saying it's useless, but we don't need to, at least here, and we'd prefer using something that's close to the physics.
Okay. I think we have time for last question, and the other question should be put in the Google Doc, please. So the last question will be: do you use more of open source satellites or combine with commercial ones?
We use both. Worldview 3, for example, is a commercial one, but for sure, Sentinel-5P and Sentinel-2 are game changers here, and they are open source satellites launched by the EU. And so Sentinel-5P in particular was a game changer, and that's open.